Hi friends, in this video let us revise analog and digital communication systems required for our TRB exam. Right? So in analog and digital communication system, we can segment this subject into following parts. One is amplitude modulation. Second one, angle modulation. Third one, digital modulation and coding. Fourth one, information theory. And fifth one is random process. Right? So such a vast topic, right? So it covers both theory and problems. Let us try to recall. In amplitude modulation, we study about AM. In angle modulation, we study about FM and PM. In digital modulation, we study about ASK, FSK, PSK, and UPSK, right, etc. Here we have to study about PCM, DPCM, delta modulation. Right, in information theory, we have to study about what is information, then self-information, then mutual information, channel capacity, and coding. Fine, in random process, we have to study about autocorrelation function and the power spectral density. So this is one of the wide topic and a very important subject also. So let us start with amplitude modulation. In amplitude modulation, we have to see what is modulation, that everyone knows, right? So modulation is changing property of carrier wave in accordance with the baseband signal. This is called amplitude modulation. Sorry, this is called modulation, right? So what is AM? AM is changing the property of carrier, changing this property. What are the properties a wave can have? They have amplitude. Any wave has amplitude, frequency, and phase. So changing the amplitude of carrier wave in accordance with the baseband. Baseband signal is nothing but our message signal. Then it is called AM. FM is changing the frequency of the carrier wave in accordance with the baseband signal. PM is changing the phase in accordance with the baseband signal, is called phase modulation, right? So these are all called continuous modulation, right? These three are continuous modulation. Why they are called continuous modulation? Because the carrier is continuous. That is very, very important, right? So next, another type of modulation is there, that is called pulse modulation. In pulse modulation, we have PAM, PPM, and PC, right? Okay. So in continuous modulation, we have AM, amplitude modulation, and angle modulation are coming under the category of continuous modulation, whereas PAM, PPM, and PCM are coming under the category of pulse modulation. Okay, fine. So next, let us study in depth about amplitude modulation revision. So in amplitude modulation, what are the things we have to know? We have to know what is the AM waveform equation. AM wave equation can be represented as S of t is equal to Vc plus Vm cos omega mt into cos omega ct, right? So here amplitude is modulator, amplitude of the carrier, cos omega ct is a carrier. So in general we consider messages Vm cos omega mt, carrier is Vc cos omega ct. So the amplitude of the carrier is modulated, that's why it is called AM wave. This is the general equation of AM wave. This I can write as Vc cos omega ct plus Vm cos omega mt into cos omega t. This is also AM wave. So I can take Vc outside, 1 plus Ma cos omega mt cos omega, right? Or I can write Ma as mu. This is mu, where mu is equal to Vm by Vc. Clear? So mu is called modulation index. Modulation index of AM, right? So if mu is less than 1, it is called under modulation. If mu is greater than 1, over modulation. Mu is equal to 1, critical modulation. Right? So this is the thing we have to remember. Then AM wave can be also written as S of t is equal to Vc cos omega ct plus MAVC by 2 cos omega c plus omega mt plus MAVC by 2 cos omega c minus omega mt. This one is carrier. This is upper sideband. This is lower sideband. This is amplitude of the carrier. This is amplitude of upper sideband. This is amplitude of lower sideband. Right? Then we should know modulation index. After that, we have to know about efficiency. Efficiency is given by mu squared divided by 2 plus mu squared. Right? So if mu increases, efficiency increases. RA. So mu is modulation index, right? Okay. Right. So that is the one thing we have to know. Mu can be written as V max minus V minimum divided by V max plus V minimum also. Right. If my signal is having more than one message, then we have different modulation index. So M1 for modulation index for message 1, M2 modulation index for message 2, Mn modulation index for message n, means total modulation index is given by M1 square, M2 square up to M1 square. This they asked in TRB. Fine. Next, transmitted power by AM is given by PT is equal to PC 1 plus mu squared by 2. Right? So it is the transmitted power. Current by AM, IT is given by IT is equal to IC 1 plus mu squared by 2, PC carrier power. PT transmitted power, IT transmitted current, IC carrier current, right? And carrier power can be written as PZ, that is equal to VC squared by 2. Sideband power can be written as MA squared PC by 2, right? So efficiency I can write in terms of sideband power and total power, where total power is equal to carrier power plus sideband power. This is what efficiency. Then bandwidth of AM is 2 omega m. Okay, so then what are the devices used for AM generation? AM is generated by 1 switching modulator, 2 square law modulator, 3 collector modulator. To detect AM, we have envelope detector, second one square law detector. In envelope detector, we have two problems. One is diagonal clipping, second one negative peak clipping. Okay, so these are all the things we must know about AM. Then double sideband suppressed carrier AM, DSBSC AM. So here we have only two sidebands and no carrier, right? So it is generated by the general equation of this one is we have to multiply carrier and message. If you multiply carrier and message, you will get DSBSC. So carrier is VC, message cos omega CT. So this is what DSBSC waveform. Okay. So we know power in double sideband is given by MA squared PC by 2. That is equal to MA squared PC squared by 4. Right? Okay. So these are all the things you must know. And DSBSC generated by, if we want to generate DSBSC, we need balanced modulator and a ring modulator. By using these two things, we can generate DSBSC. To demodulate or demodulating DSBSC, I need synchronous or coherent detector. Then another thing is there, we need co-stars receiver to nullify phase offset in DSBSC. So this is the thing we must know. Next we have to study about SSBSC AM. Here we have only one sideband, no carrier, right? So it is having a bandwidth of FM. So whereas DSBSC having a bandwidth of 2 FM. And to generate SSBSC, we have to use frequency discrimination method and phase discrimination. Right, so these are all the AM modulation we have to know. Clear. So next what I should know, VSBSC modulator. In VSBSC, so VSBSC AM, here we have V is called vestigial sideband, right? So here we have one sideband and vestige means part, vestige of another sideband. So this is what we are using in TV video, right? So in TV video signal we are using vestigial sideband. In TV audio we are using FM. Fine. Okay. Then we must know about super heterodyne receiver. In super heterodyne receiver, local oscillator frequency is given by incoming radio frequency plus intermediate frequency, and image frequency is given by 2 FRF plus 2 intermediate frequency FIF, right? So here RF stage, it will perform image channel rejection. In RF stage we have image channel rejection. In IF stage only we have amplification, filtering and demodulation. Amplification, filtering and demodulation. Right? Okay. So these are all the things we must know about. Yeah. Next we go for frequency modulation or frequency modulation, angle modulation. In angle modulation we have one as frequency modulation, second one is phase modulation. Right? Okay. So in phase modulation we have known phase of the carrier is varied in accordance with the baseband signal, right? So here one is phase is varied, phase of carrier in accordance with the message, right? So carrier phase theta I of t is given by 2 pi fct plus ap m of t, right? So angle modulator signal is given by s of t is equal to vc cos theta I. So phase modulation signal is given by SPM of P is given by Vc cos 2 pi fct plus kpm of t. Then it can also be written as another form of SPM of t is Vc cos 2 pi fct plus kpvm sin omega mt, right? Then third point, instantaneous frequency of angle modulated signal is given by fc plus kpvm fm cos 2 pi fm of t, right? So this is the instantaneous frequency. So the frequency deviation del f is equal to kpvm by fm. Then beta modulation index of the beta is modulation index of pm, which is given by del f by fm. This is kp, right? And bandwidth of this pm signal is 2 into beta plus 1 fm. In pm signal, amplitude is constant and carrier power is given by Vc squared by 2r. Okay, so these are all the things we must know about pm wave. Then frequency modulation. So in frequency modulation, what are the things we have to know? One is frequency of the carrier. Is varied in accordance with the message signal. Message or baseband, both are same only, right? Amplitude is constant and phase also, right? So next one, then carrier instantaneous frequency is given by Fi of t, that is equal to Fc plus Kpm of t. So Fm wave is given by Sfm of t is equal to Vc cos 2 pi fct plus 2 pi kf integral 0 to t m of tau dt. The other form of FM signal is Sfm of t is equal to Vc cos 2 pi fct plus beta sine 2 pi ft, where beta is equal to kf vm by fm. So kf vm by fm. This is modulation index of FM, right? Okay. So this is one of the important thing, and another thing is percentage of modulation of FM signal. Percentage modulation of FM is given by beta FM, that is equal to del f actual divided by del f max. That is actual frequency deviation divided by maximum frequency deviation. So del f max is equal to 75 kilohertz for radio, and del f max is equal to 25 kilohertz for TV, right? So here FM signal can swing from carrier frequency to, it can go up to maximum del f minimum minus del f, right? So carrier swing in FM is given by 2 del f, right? So next one is how to generate FM from PM or PM from FM. So if you are having message signal, differentiate it, right? Differentiate that message, then pass through FM, you will get PM. If you are having message signal, integrate it, pass through PM, what you get is FM, right? So this is the thing we have to know, right? So if modulation index is far less than 1, we have narrow band FM. If modulation index is far greater than 1, we have wide band FM, right? So for narrow band FM, bandwidth is equal to 2 FM. For wide band FM, bandwidth is infinity. Okay. Next one, SNR of FM, 3 by 2 beta squared. SNR of AM, 1 by 3. SNR of input. SNR of DSBSC, that is given by SNR of input only. SNR of PM is given by 1 by 2 beta squared. And another thing we have to remember is, we know AM has carrier plus 2 sideband. DSB, it has only 2 sideband. So SSB, we have 1 sideband. So it implies here P1 is more. Power to transmit AM is more. Power to transmit DSB is somewhat less. It is this one. So P3 is lesser than P2, lesser than P1. Similarly, here we know bandwidth is 2 FM. Here also 2 FM. Here FM. So from this, what we understand, bandwidth of AM is equal to bandwidth of DSB. Both are greater than bandwidth of SSB. Right? So these are all the things we must know. Okay, then to generate FM, what I need, we are having different types. So FM generation, right? So FM generation, we have direct method and indirect method. Whereas for FM detection, what are the things we have? So by using direct method, we have lobe detector, zero crossing detector, and ratio detector. Whereas in indirect method, we have PLL. Okay, so these are all the things we have to know about what you call analog modulation. So next we will see about pulse modulation, pulse coding technique. In that we have to understand what are the important things in pulse, right? So one is pulse code modulation. Second one, differential pulse code modulation. Third one, delta 1. Right? So let us see what is pulse code modulation. We know. So pulse code modulation, in this we are having some blocks. What is that is your message. First it will be sampled, then it will be quantized, then encoding will be done. Right? So this four combination this is a block of pulse code modulation. In this is happening in transmitter side, same thing in the reverse process will happen in receiver side, right? So we have one analog signal, right? So this is time, this is amplitude. So what we do, the time is continuous, we make it discrete, right? So that discretization of time is called sampling, right? So here we have 4 plus 4, 8 samples, right? So the frequency, let us assume this is 1 second. So frequency is 1 hertz, right? So as per Nyquist sampling theorem, Fs must be greater than or equal to 2f max. So Fs in theoretically it is 2, but practically I have taken 8, so it is very good to recovery. So sampling converts continuous time signal into discrete time signal. Next what I do, then you see the amplitude A. So instead of having this amplitude is continuous, instead of having continuous amplitude, I make it discrete. So this is 0 0, 4 levels. So this is called quantization. So 1 0 1 1. So discretizing amplitude is called quantization. Right. So here I have totally 4 levels. So each sample is represented by 2 bits. So how many samples I have? 8 samples per second, and each sample is represented by 2 bits per sample. So the data rate is 16 bits per second, right? So if I take 8 samples and each sample is represented by 2 things, then it is called 16 bit. So I send 16 bits per sample, and this is called pulse code modulation, right? So in PCM, what are the things we have know? In PCM, data rate is NFS, N is number of bit, F is sampling, right? So and another thing we have to know is SNR in PCM. SNR in dB is given by 1.8 plus 6n dB, right? So in this number of bits. Then what you know is we have to know step size. Step size is del squared by 12. So sorry, this is noise power. This is noise power. Noise power is equal to del squared by 12, where del is step size. The step size is nothing but interval between the two levels. So you can say this is del, right? Interval between the two levels is called step size. Okay. And the quantization error is given by del by 2, maximum quantization error, right? So that is given by del by 2. Okay, so this is the thing. In quantization we have two types. One is mid-rise quantizer and mid-trade quantizer, right? In mid-rise quantizer means the quantization will rise in the center. So quantization steps will go like this. In mid-trade, the quantization trading. So it is trading like this. Okay. So this is mid-rise and mid-trade. So then we have uniform quantization and non-uniform quantization. In uniform quantization, step size is equal step. Here unequal step. Right? So non-uniform quantization is used in speech. Right? So we have two compounding techniques. One is Mueller compounding. Mueller compounding is used in US and Japan. ELA is used in European Union and India. Right? So this is another important point we have to remember. Okay. Next, in DPCM, what is the thing? Difference between the adjacent sample is encoded. Adjacent sample is encoded. That is called a DPCM, right? Next, what we have to know is delta modulation. Here we have 1 bit per sample. In PCM, the number of bits is determined by quantization level, whereas in delta modulation, it is 1 bit only, right? So here bit rate is Fs. Okay, and here we have two important problems. One is granular noise, and another one is slope overload distortion. In what is granular noise? See, let us assume the message is somewhat low frequency signal like this, and if the quantized signal will go like this, right? So what happens? There is a approximation error between this is quantized signal, right? So if the approximation is not good, so it will lead to approximation error, right? So that error is called granular noise. Here you see this error, right? So what happens? So in order to reduce that, I have to reduce the step size. So this is a step. If I reduce step size, then it will be removed. So to avoid granular noise, reduce step size. So when granular noise happens, so when your message is slowly varying signal and your step size is large, then it will create approximation error. That error is called granular noise. Next one is slope overload distortion. So let us take waveform like this. Okay, change it. If your waveform like this and your approximator signal is like this, right? This is my M of T message. This is DM signal. Here what you see, the delta modulated signal is not able to follow the signal, right? So that is your message varies fast, your modulated signal varies slowly. So if I want this delta modulated signal touch this, what I have to do? This here I have to increase the step size. This gap is called slope overload distortion, right? So to avoid slope overload distortion, what I have to do? To avoid slope overload distortion, I need to increase step size, right? So this one will be increased. If you increase, then it will touch that. So then approximation error will be less. So mathematically, to avoid slope overload distortion, the amplitude of the message should be del by 2 pi fs by fm. So del, we know it is step size, fs is sampling frequency, f max is maximum of input frequency. Right, so these are all the things you must know about slope overload distortion. So we have next sampling. So we have three types of sampling. One is ideal sampling. Next one is natural sampling. Right, third one is flat top sampling. Right, so these are all the things we must know. In ideal sampling, the spectrum is constant. Right, so that is the one thing we have to know. Right, and regarding natural and flat top sampling, in flat top sampling, what is the thing is, here it is easier one to implement. Easier one to implement. Okay, then next one is, here top of the sample is constant. Okay, so natural sampling complex. Natural sampling is complex one, right? So in flat top sampling, we have one problem called aperture effect. Okay, so these are all the things we must know, the problems of natural and flat top sampling. So next we will go to digital modulation technique. Here we have amplitude shift gain, then frequency gain, then phase shift gain, and in phase shift gain we have BPSK, QPSK, 8PSK, like that it will go, right? So what is the difference between this modulation and angle analog modulation? Here message is digital, right? Carrier is analog only, right? So in ASK, what is the thing? So here we have two amplitude fast carrier. For one we have one waveform, for zero null, right? So suppose if you want to modulate a message 1010, how we are modulating in AM? So 1 is this one, 0 is this, again 1 is this one, 0 is this. So this is ASK wave, right? Whereas in FSK, what we do, frequency shift gain. For 1 we have one frequency, it may be a high frequency like this. For 0 we have low frequency. So the same 1010 is modulated like this. What is the thing? One is high frequency, 0 1 is high frequency, 0 is low frequency. This is FSK, right? In PSK, 1 is represented by one waveform, sin omega t, let us assume. 0 is represented by the waveform with another phase. So sin omega t plus 90 or minus 90 I put. So sin and cos are 90 degree out of phase, so I put cos omega t. So again 1 0 1 0 is represented by 1 is represented, you see 1 is represented by sin omega, right? So once 0 comes, it is cos omega. Again once 1 comes, it will be sin omega. Once 0 comes, it will be cos omega, right? So there is a discontinuity in what do you call PSK, right? So here you see in all the modulation techniques, number of bits per symbol is, so in ASK, FSK, number of bits per symbol is 1, whereas number of symbols are 2, because for 0 we have one symbol, for 1 we have another symbols, right? So that is what ASK, PSK, FSK. Whereas in QPSK, Q means quadrature. Quadrature means 4. So here we have 4 symbols, 2 bits. 2 bits per symbols, right? So we have another important term in digital modulation. One is bit rate, which is given by number of bits per symbols, number of bits per second. Second one, baud rate. This is number of symbols per second. So in ASK, PSK and FSK, bit rate is equal to baud rate. Right? So these are all the things we have to remember in all those things. Fine. And probability of error for all the things. For ASK, probability of error is 1 by 2 ERFC, 1 by 2 ERFC, 1 by 2 EB by N naught. For FSK, PE is equal to, that is probability of error, 1 by 2 ERFC, EB by 2 N naught. For PSK, probability of error is 1 by 2 ERFC, EB by N. Right, so these things are in message here. Then probability of error 10 power minus 9. This implies, right, we have one bit error in 10 power 9 bits, right? Similarly, probability of error 10 power minus 6 means we have one bit error in out of 10 power 6 bits. So let us assume it is P1, P2. So which is having least error? So P1 is less error than P. So this system is preferred. This is not preferred. Okay. So this thing we have to know. So next one is pulse modulation. Right. So in pulse modulation, what will happen? Let us see. Right. Here we have 3 types of modulation. One is pulse amplitude modulation. In pulse amplitude modulation, a series of pulses in which the amplitude of each pulse represents the amplitude of information. Amplitude of information at a given time. That is called pulse amplitude modulation. Then pulse duration modulation. Right here, a series of pulses, right, in which duration of each pulse. Here, amplitude of each pulse. Here, duration of each pulse represents the amplitude of information at a given time. This is called PDM. Next one is pulse position modulation. Pulse position modulation, it is a series of pulses in which timing of each pulse represents the information at a given time, right? So these are all the points you have to remember, right? So we have one modulation that is called pulse time modulation or pulse duration modulation. Pulse duration modulation, also known as pulse time modulation, PTM, right? So here we have two types of modulation. One is pulse width modulation. One is pulse width modulation and another one is pulse position modulation. So PPM has two types. One is pulse width, another one is pulse position modulation. So it is PWM, it is PPM. Fine. So these are all the two types of modulation we have in pulse modulation, right? Okay. So in digital modulation, we have two detection technique. One is detection technique in digital modulation, right? One is coherent detection. Second one is non-coherent detection. What is coherent detection? It exploits knowledge of the carrier phase reference. Knowledge of the carrier wave phase. Right? So that is a missed thing. It is a main point that should be noted, right? And right, provides optimum performance. Provides optimum performance, right? So that is a main thing about coherent detection. What about non-coherent detection? So when we go for non-coherent detection, so when there is no knowledge about carrier phase, if there is no knowledge about carrier phase, then non-coherent detection is used. Non-coherent detection is used, right? So that is another thing we have to know. Okay, so then one more modulation is there. It is differential phase shift gain. In DPSK, different between the symbol is modulator, right? So it is a non-coherent version of PSK. Non-coherent version of PSK, right? So, and it doesn't need synchronous detector at the receiver. Synchronous detector at the receiver, right? So this is another important point we have to talk about differential phase shift keying, right? So bandwidth of DPSK is less than bandwidth of BPSK, but probability error of BPSK is greater than probability error of BPSK, right? So these are all the things we must know about what you call digital modulation techniques. So next we learn about important topics of information theory, right? So in information theory we should know a lot of things. One is information content in a symbol. Information content in a symbol is given by symbol is I of xi, that is equal to minus log base 2 p of xi. Right? P of xi is probability of occurrence of that symbol. That I can write as log of 1 by p of xi 2. Right? So suppose if you don't know how to find log x base 2, what you have to do? This is log x base 10 divided by log 2 base 10, right? So many people have this problem, how to convert this log base 2 into log base 10, right? Not x, it is log x. Okay, so this is the thing. Then properties of information. Regarding properties of information, property number 1, information is 0 if probability of occurrence is 1. Right, the sun rises in the east, probability of occurrence is 1, so information is 0. Right, because everyone knows that, so it doesn't contain any information. Then information is always positive. We don't have any negative information, right? So information is always positive. Then information content at xi is greater than information of xj, right? If probability of occurrence of xi is less than xj. Just now only we have seen if probability is less, information is more, right? A man bites a dog, it has less probability, more information. Dog bites man, more probability, less information, right? So next one, I of xi comma xj is equal to I of xi plus I of xj if xi and xj are independent, right? Then fifth one, suppose if I of x1 and x2 is asked, it is given by log base 2 1 by p of x1 p of x2 if x1 and x2 are independent. Okay, then average information. Average information is also called entropy, which is given by the symbol h of x, that is minus I2 n p of xi log base 2 p of xi, bits per symbol, right? Next one, entropy varies between 0 to log m base 2, right? Then information rate r is given by r of h of x, right? So this is symbol rate in symbols per second. This is entropy. This is bits per second. R is equal to 1 by bit duration, right? So R is equal to 1 by Tx. Then we should know about joint entropy h of x comma y, that is given by minus g is equal to 1 to m, I is equal to 1 to m, px yj log 2 pxi yj. This is joint entropy. Next, conditional entropy. Conditional entropy is given by h of x by y is equal to minus j is equal to 1 to m, I is equal to 1 to m, p of xi yj log base 2 p of xi by yj. And conditional and joint entropies are related by h of x comma y is equal to h of x by y plus h of y. Then h of x comma y is equal to h of y by x plus h of x, right? Then we should know about mutual information. Mutual information is given by I of x colon y is equal to h of x minus h of x by y. Right? So what are the properties of mutual information? I of xy is equal to I of y. Mutual information is also non-negative. Okay. Third one, it is non-negative. I of x colon y is equal to h of y minus h of y by x. I of x colon y is equal to h of x plus h of y minus h. Right? For lossless channel, h of xy is equal to 0, because lossless means there is no loss, everything will be received, so the information is 0. Then for noiseless channel, h of x is equal to h of y, h of y by x is 0. Y by x is equal to 0. Then we have to know Shannon-Hartley theorem. That is channel capacity theorem. Channel capacity is given by C is equal to B log 1 plus SNR base 2. B is bandwidth. Right? So if they give SNR is equal to 15, C is equal and bandwidth is equal to 100K. So this is 100K log 1 plus 15, 16. So 16 I can write as what do you call 100K into log 2 power 4 base 2, 100K into 4 log 2 base 2, that is 400K. This is what channel capacity, right? So next we must know about type of channel. So for that we have to know channel matrix. Channel matrix is given by Py by x, that is equal to Py1 x1 Pyn by x. PY1X2 YNXN. This is PY1XN, PY2XN, PYNXN. This is channel matrix. So for lossless channel, the channel matrix has non-zero element in every column only. So it is 3 by 4, right? So 0, 0, 0, 1 by 4, right? 0. Here you see the non-zero matrix in every column, right? So this is lossless channel. Next one is Deterministics channel. In deterministic channel, it has non-zero element in only one row, right? Non-zero element in only one row. See, it is only one non-zero element in each row. One non-zero element in each row. Here, one non-zero element in each column, right? Okay. Third one is noiseless channel. Py by x. Only one non-zero element in each row and column. So this is noiseless channel. Then for binary symmetric channel, BSC, for binary symmetric channel, Byx is equal to 1 minus P, 1 minus. What is binary symmetric channel? The probability of receiving 0 when 1 is transmitted is equal to probability of receiving 1 when 0 is transmitted, right? So this is called a binary symmetric channel. Then we have two coding techniques, right? One is Huffman coding, channel fan-out coding. In that we have to remember something: average code word length. Average code word length L is equal to summation I goes to 1 to m p of xi n I. N is number of bits. This is probability of occurrence of symbol n. Code efficiency eta is given by minimum length divided by total length. Then code redundancy, that is given by gamma, which is equal to 1 minus eta, right? Then source coding theorem, it talks about adding redundancy, right, to avoid error. The best example is parity bit. Channel coding theorem, removing redundancy. tendency to conserve bandwidth. Okay, so these are all the things you must know about information theory. Next, in communication, we must know about random process, right? So before knowing random process, we must know random variable clearly, right? So what is random variable, right? So what is that? A function which can take any values, from sample space S and its range, right, is some set of real numbers, is called a random variable, right? So random variable of the experiment. So we have two types of random variable. One is discrete random variable. D means discrete. Second one is continuous random variable. C for continuous. Right. So what is discrete random variable? Discrete random variable which can take only finite number of values in observation interval, right? So that's why it is called discrete random variable in observation interval, whereas continuous random variable takes infinite number of values. It can take infinite number of, not times, infinite number of values in observation interval. This is another important thing, right? So discrete random variable has finite number of discrete values, finite number of distinct values, whereas continuous random variable has infinite number of values. Okay, so this one we have to know, right? So then only we can go for random process, right? So random process. So what is the difference between random variable and a random process? Random variable maps sample space into real number, whereas random process maps sample space into a function x of t. In signal form, we say sample space is mapped into signal. Here it is number. That is the difference between random variable and a random process, right? So these are all the things we have to know. So two parameters characterizing random process. Two parameters characterizing random process. One is probability density function and autocorrelation function, right? So these are all the things we have to know. And next one is ensemble. The term we use regularly in a random process. Ensemble is collection of sources. This is a very important term, right? Okay. Then next thing is what you call autocorrelation function. Autocorrelation function ACF. autocorrelation function ACF is given by, what is autocorrelation? First we must know what is correlation. Correlation is measurement of similarity between two waveforms. Autocorrelation means comparing a wave or signal with its delayed version. That is same signal. We are comparing and find the similarity between two same signal, right? Cross correlation means comparing and finding similarity between two different signals. Right? So autocorrelation we will give Rx of tau, right? That's why it is XX, cross correlation X and Y, Rx tau. So autocorrelation, this is very important. So what are the things we have to know about autocorrelation? Rx of tau, autocorrelation function of T1 and T2 is given by E of X of T1, X of T2, where T so Rx of tau I can write as Rx of tau I can write as E of X of T, X of T plus tau. So tau is T2 minus T. So here you see autocorrelation is function of tau. So Rx of tau is a function of tau. That is very important. It doesn't depend on anything, right? Tau is the interval between the two times, right? So the main properties of autocorrelation function is autocorrelation is even function. So Rx of tau is equal to Rx of minus tau, even function. Then the maximum value of Rx of 0, right? So the maximum value of autocorrelation function is Rx of 0, right? That is second property. Third one is mean square value, that is equal to DC power. DC power of any random signal is given by limit tau tends to infinity Rx of tau, right? So that is mean square. So when tau tends to infinity, Rx tau becomes mean square value, right? Then fourth one, sorry, the square of mean. Then mean square value of random process is given by Rx of 0, right? So that is given by Ex square t, right? So that is the thing. For discrete random process, this is for continuous random process, whatever the thing we wrote above. For discrete random process, Rx of k is equal to E of xn, x of nk, right? Okay, then autocorrelation is conjugate symmetry. Rx of tau is equal to Rx star tau, right? Then properties of cross correlation. For cross correlation, Rxy of tau, simply magnitude of cross correlation is given by Rx of 0 into Ry 0 square root, right? Then Rxy of tau should be having an upper limit of 1 by 2 Rx of 0 plus Ry, right? Okay. These are all the important properties. Suppose if two random signal x of t and y of t are independent, then cross correlation between those two is given by multiplication of their individual mean Ex and Ey expectation. Okay, then limit r tau tends to infinity, r xy tau is equal to limit tau tends to infinity, r y tau is equal to 0. Then r xy of tau is equal to minus r yx of tau. Right, so that is another important property. And if x of t is periodic, ACF is also periodic. Next, we have to know about power spectral density, power spectral density. Right? So, what is this? It is a representation of random variable in frequency domain. Right? So, power spectral density is given by power per unit bandwidth. So the unit is power watts, bandwidth is X. Right? So the properties of power spectral density. Power spectral density is given by Sx of f. That must be non-negative 1. Second property is it is real. Third property is Sx of minus f is equal to Xx of plus f. Sorry. So it is even function. So non-negative, even and real, right? Area under PST is given power of the process. This is another important property. Right, so suppose if they give Sx of f is equal to omega square divided by omega square plus omega by 4, you see it is even, right? So it is non-zero, right? And it is real, so it is PSD, right? So Sx of f is equal to minus omega square plus omega square plus 4, so it is negative, so it is not PSD. One property is not satisfied, second property, right? So this one we have to know, right? And autocorrelation and power spectral density are Fourier transform pair. So Rx of tau, if you take Fourier transform, what you get is power spectral density. This is called Wiener-Kirchhoff theorem. Right, so that is another important point we have to know. Okay, next transmission of response of LTI system to random process. Response of LTI system to random process. So when any LTI system is given with a random signal, LTI, what you get is y of t. This is Sx of f and this is Syi of f. So Sy of f is equal to h of f squared into Sx of f. This is h of f, frequency response. Then there's an important point. Then second one, E of y of t, that is equal to h of 0, E of x of t. Right, so this is second point, and third point is E of y of t is equal to E of X of T convolution H of. This one also you can write, right? And we know autocorrelation and perspective density are Fourier transform pair. So Ry of tau is equal to 1 by tau minus infinity plus infinity Sy of f e power minus j omega d omega, right? So this is another important property of what you call autocorrelation. Sorry, perspective density and autocorrelation. And fifth one, Ry of 0 is equal to E y square t. This is equal to 1 by 2 pi minus infinity to plus infinity h of omega square sx of omega d omega. Next we have to know about white noise. Right? So noise in ideal form. That is called white noise. Contains all frequency in equal amount. PSD is independent of frequency. So Sx of f is equal to n naught by 2 perspective density, right? And for white noise, Sx of f, it is perspective density. For this autocorrelation is n naught by 2, right? So this is another important property. And what are other things you have to know? And these are all the things you must know about white noise, right? So these things you must know before go to any exam in any competitive exam in communication subject, right? So mostly I cover all the topics, so you extend it, and these things you don't miss it. Hope it will be useful for you people. If you have any doubt, please ask in comment section. Let me clarify. Thank you.